This presentation is entitled The Influence of Electrode Wear Strength and Fracture of Spot Welds During Shear Tension Test. I'm Pasquale Russo Spena, and this work has been also performed by other colleagues from the Department of Management and Production Engineering and Politecnico di Torino, and particularly by Giulia Bruno, Manuela De Maddis, Franco Lombardi, Luigi Panza, and Emiliano Traini. In many manufacturing plants, 60% of the defective welds are due to worn electrodes. Typically, a modern body car contains from 4 to 7,000 spot welds. And so having an accurate control of the electrode wear can ensure the required quality level of a spot weld, and thus it would allow to reduce the number of weld spots needed to assemble a body car. As the number of welds increases, the electrodes damaged by wear due to different and complex electrical, chemical, mechanical, and thermal phenomena, which also interact one another. Overall, the wear mechanisms that occur on the electrode surfaces mainly cause an enlargement of the electrode tip diameter, oxidation and erosion of the electrode surface. As a result, the current density decreases, and in turn, this leads to a reduction of the nugget size, defects like voids, as you can see in this nugget, and unwelded area. And so the control of spot weld quality requires the knowledge of the weld nugget size and of the weld strength. And they are normally assessed through destructive tests. And particularly, you are not able to check any spot welds during the process, but you can check the spot welds only as a sample. This has fostered the research activity toward the implementation of many indirect measurement methods for the evaluation of the joint quality, many of them exploiting process signal curves. And so the basic idea of the work that is ongoing has been to monitor different welding signals, such as welding current, electrode displacement, and so forth, from hundreds and successive weld spots, and relate them after a data analysis to electrode wear indicators. And so from this analysis, a level of electrode wear can be selected as a criterion of some joints, and the electrodes are replaced when they reach that level that can be defined by the analysis of welding signal. Particularly, this presentation shows some partial results of this study, and particularly relative to the weld strength and the fracture mode obtained from weld spots at different level of electrode wear. Particularly, we performed hundreds of welds on several sheet stacks made of two overlapped sheets, as shown in this picture. After realizing a certain number of spot welds, we have obtained some shear tension samples in order to evaluate the mechanical strength of the spot weld. At the same time, we have evaluated the electrode wear through a carbon imprint test. In this test, a layer of white paper and a layer of black carbon paper cover completely the sheet stack. Then a weld cycle is carried out without passage of current. In this way, the electrode phase imprint remains visible on the white paper. And based on the electrode impression, some consideration of the electrode wear can be made. Particularly here you can see an example of the imprint of the new electrode tip and here the typical imprint of a worn electrode. And so, after a certain number of spot welds, we can define which is the mechanical strength of the spot weld after realizing shear tension samples. At the same time, we can define through the carbon imprint test the entity of electrode wear. And we have done this about each 140 spot welds until the electrodes was completely worn. And so the idea is starting from the new electrode, realize at first some weld samples to be subjected to the shear tension test in order to understand which is the resistance at the beginning when we have a new electrode. And after that, we have realized that this several series of spot welds, and after 140 spot welds, we have realized sample to determine the mechanical strength and a carbon imprinting test to define the electrode wear. And we have proceeded in that way until the electrodes were completely worn. And in the meanwhile, we have monitored the welding signals in order to find a relationship between such signals and the electrode wear and the mechanical resistance of the spot welds. We have carried out this activity on a dual phase steel with 1 millimeter of thickness through an industrial medium frequency direct current machine that you can see there. We employed some copper chromium electrodes with a tip phase of 6 millimeter, and here you can see the welding cycle that consists basically in clamping the sheet stack with a force exerted by the electrode of 3.5 kilonewton with a welding current of 8 kiloampere for a time duration of 300 milliseconds. And here you can see the results of the weld strength of the welded samples at varying electrode wear condition, starting from the beginning in correspondence of the new electrodes, for which we obtained a level of mechanical strength of around 10 to 11 kilonewton. And then after 140 number of welds, we have defined the new imprint test. We have realized a new welded sample for the mechanical test, and so forth, up to reaching a number of welds in correspondence of a very worn electrode, for which you can see that there is a very large scattering on the mechanical strength. In some cases, you have some joints with a strength level similar to what we have found before, but in many cases, you have a very low mechanical strength. And what we have done is to compare not only the typology, the entity of the weld strength, but also the correspondent mode of fracture occurring at several conditions that basically are represented by this region of the graph and this other region with very worn electrodes. Here you can see the results obtained after about 150 weld spots. In this case, the welded sample exhibited a strength of 10 kilonewton. This is the loading condition, and particularly this picture shows you the end of the test where we had a fracture in this region. And particularly, you can see this region by separating the two parts in this other picture. You can see that the fracture is a pull-out fracture with the joint that exhibit a very good mechanical behavior. This is the typical fracture that is required for some joints. And particularly the fractured area is completely ductile. You can see the typical appearance of such fractures. Differently, when the electrode was very worn, for about 1,000 weld spots, you can see the mechanical strength was very low. The fracture mode was completely interfacial, and so we have a separation of the joint throughout the sheet surface, and particularly by magnifying the fracture surface, you can see that basically this low strength is due to the fact that the nugget was not completely welded. You can see here some unwelded area, and only this region was welded during the joining operation. This means that in this case we have a very reduced cross section of the joints resisting to the external loading condition. The fracture also in this case is ductile, even if there is always in all the cases that we found in such condition of the electrode wear some voids. Particularly here you can see the surface of an internal void that is characterized by the typical dendrite microstructure due to the solidification of the nugget at the end of the joining process. So to make some final consideration, we have performed a study in which we want to correlate electrode wear with the quality of spot welds. And particularly, this correlation can be made by analyzing the welding signals and how they modify during the process according with the tool wear. The aim is to define an algorithm that allows to consider directly which is the electrode wear directly on the machine, in a way that the welding operator is able to identify if a joint is sound or not only by analyzing this welding data, employing them as an online non-destructive test. This is good because it allows to have an accurate prediction of the electrode wear that would lead to a just-in-time maintenance activity, and also the possibility to check each spot weld. Because when you realize the joining process and you are analyzing the weld spots, you can immediately have the welding signals, and these welding signals can be elaborated by an algorithm, and this algorithm can say you if the electrode is too worn or not, and if the joint obtained is sound or not. Thank you for your attention.